All right, well, thank you everybody for coming today. My name is Scott Stender, and we're going to speak about blind security testing and an evolutionary approach to that we'll be speaking about. Start off with who am I? I'm a co-founder and vice president of BlackHat Partners. We are a consulting company primarily, but also a product. And in my personal role, I am primarily a security consultant and researcher. I work primarily on application security, and so in my day-to-day job, I'm doing design reviews, helping people figure out how to create their products securely, and doing a lot of testing, and putting in creation of a lot of test tools. And some of the experience I've had on that is what I want to share today. And I'm based out of Seattle, Washington. So why listen to this talk, and who should listen to this talk? I think you guys can feel free to head out right after I get done with that. But the purpose of this talk is because a lot of what we do as security practitioners is creating test tools. And I will say that security, especially software security, is very difficult to test. And the people who are going to get the most out of this talk are people that are writing test tools, running test tools, in charge of creating test tools. Basically, anybody who has part of testing software as their goal. And I'm terribly sorry, we'll not have any high-profile bugs today. This will be all about theory and construction of security test tools. So the title of the talk: Blind Security Testing, an Evolutionary Approach. So blind security testing, why is it useful? Why am I talking about it? Well, it's useful because in my day-to-day job, I find it is something that we need to pull out from time to time. I think anybody will agree that the more information you have about the system, the better your security analysis of it will be. And that's the case in terms of being able to get white box analysis of, getting source code, symbols, being able to do debugging and code coverage, and all those things are very helpful for a comprehensive security assessment. But even so, blind security testing happens when you have distinctions between the engineering and the audit side of things. So in one of my recent projects as a consultant, we were hired by a large e-commerce company, and this company wanted us, and we were hired by the audit team, not the engineering side. And this company wanted us to do broad testing for audit compliance purposes across a number of their worldwide sites. So they had a USA site developed by one team, a Japanese site developed by another team, same with Europe, Asia, Africa, all over the place. There are probably about 10 different sites, all of which were developed differently. And testing for all these different sites in a blind security testing framework was rather difficult. There was, different coding styles, different problems that we were finding. We found the USA site was mostly susceptible to cross-site scripting. The Japanese site had SQL injection all over the place. This was all stuff that we had to determine using only blind testing techniques. So the ability to have smart fuzzers, smart testing frameworks that are able to act based on only what the system is responding with is something that's still useful today. But the big problem with that, and one that came out of my last year's BlackHat talk, where I spoke about internationalization, is that there are a number of test cases out there that we can find, and actually a near infinite amount, and optimizing those to be the ones that are most likely to cause security flaws is something that's very difficult, and the real crux of this talk today. The talk proposes a method of competition between test classes and test cases within those classes to optimize those test suites, and that's where the evolutionary part comes in. So this talk will be in 3 parts. The first is background, where I hope to prove to all of you that optimization is necessary, it's important, and it's something that we're going to have to do if we're going to move forward as a security industry. The next part will be current approaches, things that I've seen people employ to optimize what they have today and be able to, without anything that I'm proposing today, actually make more optimal test suites. And then the last part is what I'll propose as a framework for making smarter testing suites. There's an implementation of this that I'm working on, but it's not ready for public release. But when that is the case, I will release it. So I'll head into background. So problems testing software. The big problem is that even trivial applications can generate near infinite test cases. And even forgetting about security for a moment, just doing basic functional testing, one classic example of that sort of trivial application with a lot of tests was proposed in a book called The Art of Software Testing. It's a rather classic book in software testing, where the author, Glenford Myers, put forth a program with 5 logic paths wrapped in a do-while loop. And that loop would execute from between 1 and 20 times. So we have a little control graph that illustrates this. On the top, we have the begin state. We go through a number of conditional choices that could be driven by user input, system state, anything you want. The big thing that we're worried about is that at the bottom, we get into 5 states, A, B, C, D, and E. You could call those the output states. So when the program hits there, it says, hello, my iteration printed out A. And then we go into the end loop. And then we terminate after between 1 and 20 executions of that logic flow. So this simple example can be represented in 10 or 20 lines of C code, or one really nasty line of Perl. And on each loop iteration, output will depend on those 5 input states. So we could say that one output of this program would be the letter B, if the loop only iterated once. If it iterated 5 times, it would be B, C, A, D, E, or something along those lines, and on up to a string of 20 characters. So if we were to have our test suite optimized around, we want to test every potential output of this application. If we were to test for 1 iteration, it would be 5 outputs that we'd have to test. 2 iterations, we'd have 30 potential outputs, 5 to the first plus 5 to the second. And if we were to go to up to 20 iterations, what Mr. Myers put forth, we'd have 100 trillion test cases. Which if we were to execute one of those per second, starting now, it would take 3.2 million years for that test suite to run. And our evil robot insect masters at that time would be very happy with our output coverage, but they'd be unhappy because they could not say that the program was correct. Because even if we've covered all the output, that is not necessarily something that assures that we've covered all the input or all the internal state. What happens if we run that again on a hot day or a hot 3.2 million years? The CPU might act differently. We might fail in another way. And if we were to think back at this same flow, this might be something that builds a number of different database executions. So, we would output, hello, this table should now have a new row that says A. This table should have a new row that says B. We could cover all this comprehensively, have 100% output coverage, 100% code coverage, and still never find the SQL injection in that. So there is a lot that we are not taking into account in terms of system dependencies and all those other crazy things. How hot it is today. If 10 inputs map to 1 output, the big takeaway is that we have a lot of functional tests to execute. Now, security testing is even harder, because what we looked at just there was an exercise in functionality alone. And security testing has 2 aspects, both functional testing and I would say non-functional or negative testing. So a functional security test case would be something like logging in to a web application. So we're presented with a form, username and password. There are 4 states we need to check for. There is, if I put in a valid username and password, I should get access granted. If I put in an invalid username and a valid password, I should get access denied. Same vice versa. And if I put in a valid or invalid both password and username, I should get access denied. So there's my functional test case for making sure that my authorization or authentication mechanism works properly. So all right, 4 cases, I'm done, I can go home. But then there's the non-functional aspect of it, where the assertion we need to do is that there is nothing under the sun that can possibly make one get past that login page and access the website without typing in a username and password. And so that involves not only trying those 4 cases, but also every piece of input, every system state, every environmental condition, anything that could possibly result in that not working. So we have, in addition to the 100 trillion test cases we spoke about a moment ago, we have a potentially even more infinite, if there is such a thing, but a near infinite set of test cases of everything that could possibly happen to that site. So we say, we have patterns. We know that if we want to get past that front page, there are things we can do like SQL injection, buffer overflows, session hijacking, a number of attacks that as security practitioners we test for. So let's go and drill down into one of those things that we need to test for if we want to have a comprehensive test. So buffer overflows are great goat because they have been known for 30 years. They've been taking down the internet for almost 20 now. And it's something that we all test for, and we all see on the news headlines every day. So what do we do when we want to test for buffer overflow? Well, the first thing is we show up and we ham-fist the keyboard for a while and make a string, hit enter, and see if it blows up. And it's unfortunate that a lot of times that is the case. But if we want to be a little bit more comprehensive, what we do is we supply a number of long strings, 128 bytes, 256 bytes, 65,536 bytes. The big thing is that there's a bunch of magic links around powers of 2. So if we say, we're going to try powers of 2, 2 to the first through 2 to the 32nd, and a few magic numbers around that, hey, that's a pretty good test suite. We send a bunch of A's into it. Well, I've actually heard of application developers who have a consultant or an external researcher find a flaw where they put a bunch of A's into a buffer and they show that EIP equals 41414141. So to fix that, what they do is they check for AAAAA and then kick it out. So if you want to test for that as well, and that's a real story, but if you want to test for that as well, you have to test for BBBBB for those same things, right? And then what happens with all those other off-the-wall things? Those of us who've been in code review for a long time have seen those crazy structs where there's 436 bytes to a struct, but if but there's a validation routine that says, hey, if this thing is greater than 430 or 440 bytes, then we'll kick it out. And so there's this magic number of 437 to 439 byte strings that will cause an overflow and cause bad things to happen. So we have to test for all those too, right? And then there's pattern-centric stuff. So if the first byte must be, in order to get that buffer overflow, the first byte of the string must be hex 1E. And then we must have a file path after that. And then the subfolder specified in that file path must be over 64 bytes in order to overflow that. So you have all these crazy things. If we really wanted to come up with a comprehensive buffer overflow test, clearly this exercise could go on and on and on until we have, yet again, another near infinite test set. And then that's just for buffer overflows. Next up is SQL injection, XML injection, cross-site scripting, attacks against custom serialization, all the other things that we find on a day-to-day basis. And then when we're done with those, don't forget random fuzzing because we find bugs with that too. And so you have a energy in the universe amount of testing you can do with random data. So what I'm trying to get across here is the need for optimized test suites. We cannot test everything. Anybody who says that we can do a comprehensive security test is lying and selling you something. So let's get away from that. What we need to do is be smart about the tests that we perform because in every instance there is a logical limit of the amount of effort we can perform, whether it's money, time, anything. We have to find the most bugs that we can in the time that we have. So if we were to think about optimized test suites, we know that today experienced security testers do this. So go back to the web application test, which I will go back to that a lot because it's a great familiar framework to discuss these flaws in. But the first thing that any security tester does when they show up at a web application is they type in an apostrophe into that login form. And if it blows up, you see a SQL exception, then hey, great, I found a bug. And the second thing people might do is type in ZZZZZ or some other recognizable pattern into the username and then see if it gets reflected back to them. And if it gets reflected, then hey, I'll go start testing for cross-site scripting attacks. Today, as security testers, we do a natural optimization. We know that a web application is going to be probably more susceptible to things like SQL injection, cross-site scripting, cross-site request forgery than it would be to buffer overflows because most web applications are written in managed languages. So this optimization happens today, but what we want to do is be able to see if we can automate it, make security test frameworks smarter. So I hope everybody's convinced that security testing is hard, that there's a lot of work to be done, and that we need to optimize things. Now, I'm not the first person to realize this, so we're going to go into current approaches. A lot of other smart people have been working on this for a lot longer than I have, and so we'll see how other people have approached this. So if the goal is optimized test cases, then we can look at most security testing tools and realize they pull from two rather large pools of test cases. First would be flaw-specific testing. The second would be random-based testing. I'll go into that a little bit. So with flaw-specific testing, the goal is to identify specific known classes of flaws. So for example, SQL injection, if I were to do a flaw-specific test for that, I would say, my test case is find a parameter in some web request or arbitrary request that might have a database behind it, put an apostrophe in it, and if I see an exception come back or some other undefined system behavior, then I think that, maybe that's a bug. Maybe I'll go file it as a bug